Welcome back. This will be a short video lecture on section 4.5, Making Connections. I've taken this section and I've divided it up into 4 subsections: connecting the dot plots, types of distributions, randomization dot plots, and finally, which technique. Let's begin with connecting the dot plots. Now let's begin by studying this problem. Herman claims that he can predict the outcome of a coin toss. Let P denote the proportion of times that Herman is correct when guessing the outcome of a coin toss. A statistician conducted an experiment with Herman. In 25 tosses, Herman was correct 16 times. Use this data in each of the following cases. First, construct a 95% confidence interval for P. Second, test the null hypothesis that P equals 0.5 versus the alternative hypothesis that P is different from 0.5, and do this at the 5% significance level. And then finally, in part 3, we're going to ask, how are these connected? So let's begin with the construction of this 95% confidence interval for P. Let's go to StatKey. We're doing a bootstrap confidence interval for a single proportion. And we're going to edit the data to reflect Herman's experiment. He got 16 out of the 25 correct. We can build several thousand samples in our bootstrap dot plot to get a really good idea of where the values of P hat are going to land. And when we hit two tail, StatKey will automatically carve out the middle 95% for us. And so we are 95% confident that Herman's proportion P is landing between 0.440 and 0.840. So that's our 95% confidence interval for the true proportion P. All right, let's head back and look at part 2 of this problem. All right, let's take a look at part 2. We want to run a hypothesis test. The null hypothesis is that P equals 0.5. That's Herman is merely guessing, versus the alternative hypothesis that P is different from 0.5. And we want to run this test at the 5% significance level. Now, the one thing we want to pay attention to is that this is going to be a two-tailed test, right? We're testing P is different from 0.5, or P is not equal to 0.5. So we'll pay attention to that as we run our hypothesis test. Now, we're going to keep the results from our bootstrap confidence interval, and we're now going to do a randomization hypothesis test for a single proportion. And there's 2 things we want to do. We want to first put in the results from the one trial that was run. Herman got 16 correct out of 25. And we want to make sure that our null parameter is set at, in this case, P equals 0.5. All right, we're going to generate several thousand randomization dots in our dot plot. And now what we need to do is look at the particular P hat that we found, right? Herman had a P hat of 0.64, and we need to know how much weight do we add, or how much weight do we attribute to that observed statistic. So let's first calculate how much is in the right tail. We'll edit this to the observed statistic of 0.64. And we can see that about 11.3% of all the dots are as extreme as 0.64. Now, we have to go into the left tail. This is 0.14 units removed to the right of the null parameter 0.5. We need to find 0.14 units removed from that null parameter in the left, and that'll be at 0.36. So in the left tail, we'll want to find 0.36. And we can see that these should be close to each other because of the symmetry of our dot plot. And we're seeing about the same thing. About 11%, a little more than 11% is showing up in that left tail. So together, that's going to give us a p-value. Let's call it 23%. All right? We don't have to be too careful here because that's a large p-value. And we're working at a 5% significance level. So at a 5% significance level, we are going to fail to reject the null hypothesis, right? There is not enough evidence, there is insufficient evidence to support the claim that Herman is doing better or different from just guessing, right? The data is just not supporting that alternative hypothesis. So we're going to fail to reject the null. Finally, let's work part 3. How are these connected? How is the confidence interval we calculated in part 1 related to the hypothesis test that we ran in part 2? So let's remind ourselves of what we found. When we constructed our bootstrap confidence interval, we had 95% confidence that the true parameter p lands between 0.440 and 0.840. Now, one of the things I want us to observe is the null parameter p equals 0.5 is in this interval. In other words, we could say that p equals 0.5 is plausible, right? We have 95% confidence that p lands in the interval from 0.440 to 0.840. So p equals 0.5, since it's in this interval, is plausible. Now, when we think about what a hypothesis test is asking us to do, we're only going to reject the null hypothesis when this becomes implausible. And what we're saying is the result of our confidence interval is showing us that p equals 0.5 is not implausible. And so it is not surprising that we failed to reject the null hypothesis in part 2. P equals 0.5, at least from what we discovered in our confidence interval, is a plausible value. It is not implausible, and therefore we will fail to reject the null hypothesis. So let's articulate a general principle, right? We can find connections between confidence intervals and hypothesis tests. The formal decision to a two-tailed hypothesis test is related to whether or not the null parameter falls within a confidence interval. When the parameter value given in H0 falls outside of a 95% confidence interval, then it is not a plausible value for the parameter, and we should reject the null hypothesis. We should reject H0 at a 5% significance level in a two-tailed test. However, when the parameter value specified by H0 falls inside of a 95% confidence interval, then it is a plausible value for the parameter, and we should not reject H0 at a 5% significance level in a two-tailed test. And this second case is exactly what happened in our experiment with Herman. We found that after conducting finding the 95% confidence interval, we found that p equals 0.5 is sitting within that confidence interval, and that makes p equals 0.5 plausible, right? It is a plausible value, and therefore we should not reject the null hypothesis at a 5% significance level. Now, if we were to change this 95% to 90%, then we would have to change this corresponding significance level to 10%. In other words, these two values should always add up to 100%. So a 99% confidence interval would correspond to a 1% significance level. So we can use this result in a wider sense as long as we're willing to make sure that these two values are always tuned to each other. These should always be complementing each other, always adding up to 100%. Let's take a look at one more example of this. So this is some data we've actually looked at before, but let's familiarize ourselves with this once again. So let's let mu sub A and mu sub S denote the mean times to commute to work in Atlanta and St. Louis, and this data is collected in minutes. The question before us is, are mu of A and mu of S different? So our first task is going to be to construct a 95% confidence interval for the difference in those means, mu of A minus mu of S. And in our second test here, or in our second step, we're going to do a hypothesis test where the null hypothesis is that mu of A minus mu of S is equal to 0. In other words, those parameters are equal. Versus the alternative hypothesis, which is mu of A minus mu of S is not equal to 0. And we'll run that at the 5% significance level. So let's first construct our 95% confidence interval for mu of A minus mu of S. All right, let's go to StatKey. Bootstrap confidence intervals, confidence interval for difference in means, And let's load our data set. And there's our original sample. And we can see, right, in this original sample that there is a difference in the commute times. At least in the sample, we're seeing about a little over a 7-minute difference in commute times. And what we want to know is, what does that tell us, right? What is this data set telling us about the difference in mu sub A and mu sub S? So we're going to generate several thousand bootstrap samples. We'll develop this bootstrap dot plot. And now what we'll do is hit toTail, and we'll come to the conclusion that we are 95% confident that the difference in mean commute times, Atlanta minus St. Louis, is covered by the interval from about 4.985 to 9.362. Now, one of the things we want to take away from this as we're heading over to do our hypothesis test is that the null parameter in this case is 0, right? The null hypothesis is that mu of A minus mu of S is equal to 0. And what we're noticing here is that 0 is not inside our 95% confidence interval. So, according to our general principle, when that null parameter is falling outside of the confidence interval, it is considered implausible, right? The null value of 0 is implausible, and that should cause us to reject the null hypothesis and lend our support to the alternative hypothesis, at least at the 5% significance level. All right, now let's go ahead and conduct that hypothesis test just to see if it's confirmed, right? So we're going to go to randomization hypothesis test, test for difference in means. We're going to want to load our data. And now we're going to look at it through the lens of a hypothesis test. All right, so under the null hypothesis, which is set here, mu1 is equal to mu2, the mean commute times are equal. We're going to generate several thousand samples. We're going to build up that dot plot. Now, what we want to do, we have to run a two-tailed test. What we need to do is look at what we observed. We observed a difference of 7.14. So I need to first calculate in the right tail how many dots exceeded 7.14. And the answer is 0, none of them, right? This is telling us in the 6,000 times, right, that we ran created a dot in this dot plot, out of the 6,000 times that we did this, not one time did we see a dot as extreme as 7.14. So the p-value is effectively 0, right? Now, technically, I should go over here and do a left tail calculation as well. I should find negative 7.14 and count the number of dots that have fallen to the left of negative 7.14. But really the point is moot. We're not going to see a dot as extreme as that in the left tail either. So the p-value, right, is effectively 0. And that means we're going to reject the null hypothesis and lend our support to the alternative hypothesis, right? So there, in fact, is sufficient evidence to support the claim that the difference in the mean commute times, Atlanta minus Seattle, is different from 0. And the point of this exercise was to draw our attention to this general principle, right? That we already had enough information in our bootstrap confidence interval to know, right? We knew that it was just not very likely that the null hypothesis would be supported, right? The null parameter was not falling inside our confidence interval, and so it was not surprising that we would find an extraordinarily small p-value and that we would reject the null hypothesis. Okay, so this was just another exercise in this basic principle. We've seen an example now where the mean parameter has fallen outside of our confidence interval, causing us to reject the null hypothesis. And we saw an example, our first example with Herman and the coin was an example where the null parameter fell inside the 95% confidence interval, and therefore we did not reject the null hypothesis. All right, our next topic is to consider different types of distributions that we've encountered. Now, in the course of our studies in chapters 3 and 4, we've encountered 3 different types of distributions. And as we're closing out chapter 4, it's a good time to go back and take a look at each of these distributions, right? So the first thing we encountered was what's called a sampling distribution. A sampling distribution shows the distribution of sample statistics from a population and is generally centered at the true value of the population parameter. Now, the problem we have with a sampling distribution is that it's very hard to get your hands on because you have to actually sample from the entire population in order to build up a sampling distribution. All right, the next type of distribution we encountered was a bootstrap distribution. So a bootstrap distribution simulates a distribution of sample statistics for the population, but is generally centered at the value of the original sample statistic. And so we can think of a bootstrap distribution as somehow standing in as a surrogate for a sampling distribution. And we use that to great effect in Chapter 3 when we built confidence intervals. All right, so the bootstrap distribution is allied to or connected to building confidence intervals. The last type of distribution we encountered was what we can call a randomization distribution. And a randomization distribution simulates a distribution of sample statistics for a population in which the null hypothesis is true and is generally centered at the value of the null parameter. And this is what we used in conducting hypothesis tests. So randomization distributions are associated with hypothesis testing. Now, we've spent most of our time studying bootstrap distributions and randomization distributions. So let's take a look at each of these. All right, here's an example of a bootstrap dot plot. And what we're seeing here is that the sample statistic, in this case it's a sample mean, is at 29.11. And this is reflected in the bootstrap dot plot. That is roughly the center of the bootstrap dot plot. So remember that a bootstrap dot plot is generally centered at the value of the original sample statistics. So we should see harmony between these values, okay? And that's typical of the bootstrap dot plot. Now let's take a look at a randomization dot plot. Here we're expecting the dot plot to be centered at the value of the null parameter. So in this case, this is a randomization dot plot where the null hypothesis is that p, some proportion, is equal to 0.5. And we can see that reflected here, that the center of our randomization dot plot coincides with the value of the null parameter and not with the statistic. Okay, so if you saw out of context a randomization dot plot or a bootstrap dot plot, you would have some clues as to which is which. You'd look at the center of the dot plot and you'd see, is it coinciding with the value of the original sample statistic, or is the center of the dot plot coinciding with the value of the null parameter? Our next topic is randomization dot plots. Now, back in Chapter 3, we learned how bootstrap dot plots are constructed, but we haven't talked yet about how a randomization dot plot is constructed. So what I want to do is show you a very, very simple example just to show you some of the basic principles that underlie the construction of a randomization dot plot. Now, in this experiment, 10 males and 10 females were gathered randomly, and they were asked to report the number of hours spent watching videos each week. And so we can see the results here. The set labeled M is for the males, and the set labeled F is for the females. We're going to look at this data in StatKey in just a second, but one of the things we can extract at this point is that the average for the males is 10.6. So 10.6 hours per week for the males in the sample. And for the females, we're seeing an average of 5.2 hours per week. So we're certainly seeing a difference in the sample means, right? The sample means are suggesting that the men are watching more hours of videos per week than the women. So, but is there a difference between mu sub m and mu sub f, the underlying parameters? So the question, though, is how do we create a randomization dot plot for the distribution of x bar sub m minus x bar sub f, so the difference in the sample statistics, under the null hypothesis, which is that those underlying parameters, mu sub m and mu sub f, are equal, right? How do we create that randomization dot plot? Let's go to StatKey and look at the data. Now, I've taken the liberty of loading this data into StatKey ahead of time, and we can see the original sample over here. The males are labeled with M, and their data points are showing up in yellow. The females are labeled with F, and their data points are showing up in purple. And so StatKey automatically treats this group as group 1 and this group as group 2. And we can see that the difference in their sample averages is 5.4. Now, what we're concentrating on here, though, is how is this original sample being used to generate randomization samples? So let me generate a randomization sample for you. What we want to figure out, and it's going to be easier at least at first to use a different tool to show how this is being done. What we want to figure out is how is this original sample being used to generate a set of dots like this in our randomization sample. Now let me show you how this is done using random.org. So I've gone to random.org and I've taken the liberty of loading our data set into random.org's list randomizer. Now, let's understand what this data set is telling us. So every case in this data set is bearing two values. One is this categorical value of M or F, depending upon whether the case is a male or a female. And then one quantitative value, which is the number of hours that particular case spent watching video hours that week. All right, so we have this male who is reporting 25 hours a week watching videos. And if we scroll down here, we can find a female who is reporting 16 hours per week watching videos. So this is our original data set. It's got a categorical value and a quantitative value associated with each case. Now, the null hypothesis is asserting that there really is no difference, at least from the point of view of watching videos, between males and females. Their habits, their video watching habits are the same. And so the assertion of the null hypothesis is that whether or not this particular data point, the 25, is attached to a male or a female is somewhat random, right? It's just chance. So there is no difference between males and females. That 25 could just as easily be associated with a female as with a male. And so one way we can take advantage of that is to take this list of 20 and randomize it, produce a randomized list. So I'm going to hit the randomize button here, and it's going to take those 20 entries and it's going to produce a randomized list of 20. So what I can effectively do is use the null hypothesis to my advantage and say, look, if there really is no difference between males and females from the point of view of watching videos, then I can take my list of 20, I can take the first 10 that appear in my randomized list, and I can call them the male group, and I can take the last 10 that appear in this list and call them the female group. And under the null hypothesis, that would be fair because there is no difference between males and females. These categorical labels of M and F are just arbitrary. So once again, I take my original data set, I randomize it, I lop off the first 10 and I call them males in my randomization sample. I take the last 10 and I call them females in my randomization sample. And then I color these values yellow and I color these values purple. And that's how I produce my randomization sample. So when you're looking at a randomization sample, every one of the dots that's appearing down here is related to a dot that's appearing up here. The only thing that we're doing is we're taking all of the dots in our original sample, we're lumping them together, we're separating them out again into two sets, we're coloring one set yellow, we're coloring the other set purple, and then we're showing them down here as a randomization sample. And so that's how these randomization samples are being generated. Every time I generate another sample, it's a lumping together of all the data, a separating out into two sets randomly, and then a coloring of those data points, either yellow or purple. A recoloring is probably a better way to say it. So that's how these randomization samples are being generated. The only advantage that's the simple procedure for doing this. Now, the advantage that StatKey has is it can just do this very, very quickly. It's a computer, so it can generate these randomization samples by the thousands very quickly. It would be laborious to do this by hand, but in principle, everything that StatKey is doing, we could do by hand, all right? That's the main thing to take away from this, that these randomization samples are not as obscure as they might seem, okay? And we're really using the null hypothesis to its full extent to allow us to clump all the data together and then re-separate it and recolor it, all right? Because if there is no difference between males and females, then the attribute male or female is random with respect to the data values. All right, so that's how these randomization samples are being generated. Let's head back to the class notes and take up our last topic, and this is the topic of which technique. Now, throughout chapters 3 and 4, we've been studying inferential methods in statistics, and that's the art of making conclusions about a population from information that's contained in a sample. And we've got two basic tools at our disposal. We've got confidence intervals and hypothesis tests. So as we draw a close here on chapter 4, it's helpful to look at some scenarios and ask, what would be the better inferential method, right? Should we use a confidence interval or a hypothesis test to settle a kind of a research question? So in each scenario, indicate whether it is best assessed using a confidence interval, a hypothesis test, or whether statistical inference is not relevant to answer it. So let's take a look at scenario 1. We want to estimate the proportion of infant car seats that are installed correctly using a sample of new parents leaving the hospital. So we'll have information from a sample. We're going to look at a sample of parents leaving the hospital, and we're going to look at the proportion of those new parents that correctly install the car seat. But we want to make an estimate about that parameter within the population as a whole. And since we're estimating this proportion, the tool here, the best tool for this is going to be the confidence interval, because it's going to locate that parameter with a high level of confidence in some interval. All right, so this is clearly best settled by a confidence interval. Let's look at scenario 2. We want to look in the U.S. congressional record to see what proportion of times a senator was absent for a vote during the previous year. Now, this is a case where I claim inference is not needed at all, because we can examine the entire U.S. congressional record for the year and count the number of times that the senator was absent for a vote during that previous year and quickly calculate that proportion. So we can have knowledge of the parameter just by scanning the entire U.S. congressional record. So inference is not really needed here in scenario 2. Finally, let's look at scenario 3. Use the sample from part 1 to determine whether the proportion of car seats installed correctly differs between two of the leading infant car seat brands. And so we have to imagine that there's maybe a brand A and a brand B, and we're going to go back and look at this data, and we're going to see the proportion of time that brand A was installed correctly. We're going to see the proportion of times that brand B was installed correctly. And what we're trying to do is use that information from the sample to see if, let's say, brand A is installed at a higher proportion than brand B in the population as a whole. And so we're being asked to conduct a hypothesis test. We're being asked to judge between these two brands for their ease of being installed correctly based on what we're seeing in the sample data. So that's a case in scenario 3 for a hypothesis test. All right, now that brings a close to section 4.5, and this brings a close to chapter 4. So the next time I'll see you, we're going to be in chapter 5. So until then, take care and be good.